the Chinkuba and also the conference community members. I could learn a lot from such impressive lecturers with different academic backgrounds. I'm going to talk about the application properties of using NIR imaging method to monitor the water content in wood during drying process. As you know, wood has been used for thousands of years because it has substantial benefits over other building materials. It is naturally renewable and helps to against climate change through carbon storage. However, despite these attractive properties, wood materials are used only to a limited extent in industrial applications compared to steel and brick. Not only because wood material has a complex tissue that suffers from poor dimensional qualities, including swelling, shrinking, and twisting, but also because wood material is hygroscopic. That means it exchanges water with its surrounding environment and resulting in changes of mechanical properties. In order to earn a stable mechanical property, an extremely important process is drying the felled wood. Otherwise, the built house will deform or even collapse. The traditional method is just to put the felled wood outdoor and just wait for it to be dried before using it. However, because such natural air drying method is time-consuming, nowadays it's difficult to only rely on it to meet the demand for mass production in the wood industry. In fact, almost half of the felled wood here is drying by artificial heating systems. Water in wood is generally classified as either free or bound water. Here, free water is considered as liquid water located in the lumens and the intercellular spaces of wood, whereas the bound water is the water that held by the intermolecular forces between the major chemical components of the wood cell walls. It is not surprising that such strongly bonded water has profound effects on its strength and stiffness. The visualization of the moisture content in the drying process is highly required and important for both theoretical studies and industrial applications. NIR hyperspectral imaging method can capture a large number of images at different wavelengths. It provides a spectrum at each pixel and enables quality evaluation across the entire surface. Compared with traditional methods such as microwave and nuclear magnetic resonance, the advantages of the hyperspectral imaging method include low cost and can provide the real-time understanding of water distribution. 3 species were selected in this study, including softwood Japanese cedar, hardwood beech, and Japanese ash. 12 samples of each species were prepared, and the size was around 24 millimeter, 12 millimeter, and the thickness was around 5 millimeter. The tissue structure of the softwood is very simple. More than 90% are occupied by tracheids. On the other hand, the tissue structure of hardwood is more complex. It has many types of cells, and the functions of each cell are also different. Besides, it is often difficult to distinguish between early wood and late wood. Here, early wood is the part where the tree grows faster at the spring and summer seasons, so the cell wall is thin and large, thus the surface color is brighter. On the other hand, the late wood part is the growth of the tree slows down. So the thickness of the cell wall is becoming thinner and the color is becoming darker. This repetition becomes the annual ring of the trees. For the experimental method, during the air drying of the wood samples, they were weighted before and after collecting the spectroscopic images and used to calculate the reference values of water content. Each sample was measured a total of 12 cycles. To calculate the different spectrum, the same samples in completely dried state were also measured finally. In this study, the wavelengths in the range from 1000 nanometer until 1850 nanometer were selected because the signals at longer wavelengths were noisy, caused by the extremely high moisture content used in this study. The distance between the target and the camera was manually adjusted to achieve a field of view of around 20 millimeter. So the spatial interval of 62.5 per pixel millimeter, micromillimeter, sorry. Each sample was positioned on a moving slider, then scanned line by line. The movement speed of the slider was set to 9.3 millimeter per second, and the exposure time was 6 milliseconds. Then the measured water content reference values were used to establish 3 calibration models with the averaged NIR spectra that collected from its entire sample surface. Smoothing and standard normal varied spectral pretreatments were used to correct for the baseline offset. The region of the wavelength around 1450 nanometer was assigned to the first overtone of the OH stretching vibrations. The one-out cross-validation was used to test the constructed the water prediction models to avoid overfitting. The PRS factor should be controlled as low as possible. It will help to improve the reproductivity of the image processing results after the PRS modeling construction. All the 3 calibration models were constructed with the LV numbers under 5. Then the 3 calibration models were repeated to multiply the NIR spectrum contained at each pixel position of the hyperspectral imaging data for the mapping purpose of moisture content. In this slide, from top to the bottom shows the 3 different samples, and from left to right shows the change in their moisture content during the drying process. The reference values are shown at white color. It is evident that the early wood part had more water compared to the later wood parts initially. This could be caused by the thin wood cell wall in the early wood parts, which has a larger space in rumens. In addition, the edge of each samples were firstly to dry, and the late wood part dried lastly because of its strong water absorption capacity. However, the traditional PRS regression analysis method can only express a collection of different types of water. But the water in wood is generally divided into free water and the bound water. The change of the free water actually has no effects on the wood materials itself, but the change of the bound water will cause the wood swelling and shrinking. Thus, during the drying process, it is desired to know the distribution of the free and the bound water. Due to the free water and the bound water have different vibration frequencies, so we studied to look for the shift on the absorption wavelength of the water in the NIR spectrum. After spectral pretreatments, it was confirmed that all the 3 different samples have a wavelength shift at about 1450 nanometer during the drying process. It shows that the vibration frequency of the OH groups in the sample changed from faster to slower, which is in agreement with the fact that the drying process generally changed from free water to bound water. Then we started to perform principal component analysis on this band. It shows that the PC1 loading and the NIR spectrum had similar shapes. This means that the PC1 loading mainly correlate with simple water content by mass in the wood samples, whereas the PC2 loading suggests more detailed interactions between wood and water. Combining the existing knowledge, the three curve peaks can be interpreted as follows. The first positive peak at wavelength around 1,400 nanometer could be due to the free water. The negative peak at around 1,470 nanometer could correlate with the weakly bound water with less mobility. And the second positive peak at around 1,550 nanometer could correlate to water that is strongly bound with the wood cell wall. Because the PC loading can be understood as the weight for its different spectrum, the relative variation of free and bound water in wood could be explored for PC scores. It is evident that the first PC score decreased from right to left during the wood drying, while the second PC score fluctuates up to down. It shows that the water in wood could have at least two types. Combined with the existing knowledge about the wood drying, the water was classified into free water, weakly bound water, and strongly bound water. Through this classification method, imaging analysis based on the PCA was performed again on the hyperspectral imaging data. Here, the red color suggests that inside the pixel area, the water mainly tightly attached to the wood cell wall. Blue color means the water can still move freely in the wood. The early wood part region of the Japanese cedar had a very high moisture content in the initial stage of drying, so here is a lot of free water. But the free water dried more rapidly than other regions. The edge of the samples dried most rapidly into the strongly bonded water. The same analysis could also be used for determining the water structure in the other two hardwoods. In this way, it provides a more intuitive parameters in the wood drying process. The summary of this study, we aim to establish a method that can quickly and non-destructively evaluate the water content in wood and the molecular dynamics of free water and bound water by NIR imaging analysis. A series of experiments have shown that the period regression analysis could determine the water distribution in wood by mesh, and the PCA method could show the distribution changing from free to bound water during drying. That is all of my presentation today. Thank you very much for your kind listening.
Thank you for your presentation, Professor Ma. Now, paper is open for discussion and any other comments? Do you have questions? Please, Elena.
So I was just wondering, because this is connected a lot with the food structure, for example. So what is the influence of the, not structure of the cells, but if you would have channels, for example? I mean, if you think about the channels in this, like in polymers also. I'm not sure. I didn't put my question nicely. So what we saw, for example, with food, the way the channels in this, let's say, or how can I say, the way the pores in the food have shape in the space, not only 2D structure, not only like cells, but the fibers, how they go. They actually, this curvature in space also influences the way the water is going to behave. So I was wondering, do you have comment on something like that in regard to your samples?
Yes, thank you very much for
Thank
your
you.
question. Yeah. Yes, I think if we just focus on the bound water, we can still separate the bound water into several types. So if if we can separate the bound water into several types, then different bond types, you can find they actually bound to the different position of the cell walls. So the physical structure will actually mainly affect the position of the bound water. But this study is actually the main purpose is just to separate the free water and the bound water, the two types. So the physical structure actually, we try to give the more information to explain the difference between free water and the bound water. So the physical structure actually we did not discuss about the physical structure effects.
So just one more question.
Yes.
Did you maybe do some kind of reference measurements with, for example, hardness of the wood, some physical properties? Because that would be interesting to see how it correlates with the water structure. Also, for example, I'm not sure how it's, but something like wettability, for example, of this surface of the wood and so on.
Yes, thank you very much for your suggestions. Actually, the bound water has a very high correlation with the mechanical properties of the wood. So after the air dried of the wood, so the wood, the stiffness will be increased. So I think, yeah, the next topic, or I'm interested to do only focus on the bound water and to check the correlation between the bound water and the stiffness of the wood.
Oh, that's beautiful.
Yeah.
Thank you. Thank you.
Thank you very much.
Any other questions? Please.
I have one question. It is a very interesting work, and drying the wood is similar to drying the food. And I can see in the spectra a typical cell spectrum pattern. Professor Ma, do you have how many different types of drying do you have? You're talking about air drying, but
yes, yeah.
I think those different types of drying relate to the way you get rid of these free water molecules. Or really, do we really want to get rid of these free water molecules? This is a very interesting question, I think.
Yes, thank you very much. Yeah, in this study, yeah, we used the air drying to build the calibration model. Now, the students in our lab, they are also trying to use the artificial heating oven to dry the wood. Also using the microwave. So it's like a microwave oven to dry the wood. Then to check the moisture content, the changing, like characteristics difference.
Yeah, the old, if I remember well, I'm not sure though, the old Europeans, and I think Schauberger also, kept the wood into the water to dry it.
Mm-hmm.
And that was the most striking thing I have ever heard.
Mm-hmm.
Have you heard about this? That you keep the wood I mean the people that use wood for temples, they like natural drying kind of. They don't push. Why it is so?
Yes. Yes, because is air drying. I mean, the natural drying is eco-friendly. Also, the damage on the wood materials is less than the artificial heating drying. The problem is now because the wood industry, they need the drying efficiency. So the heat drying, I mean, artificial heat drying is increasing year by year. So they try to heat using the heat to dry the wood faster.
Yeah.
But the problem is if you dry the moisture faster, so the wood itself, the shape will be changed.
Yes.
So we need like a monitoring technology to check the water content, changing characteristics. We try to take the balance, between the efficiency, also the high quality of the materials.
Yes. Yes. Yeah, this is my message. Use water spectral pattern as a feedback to control the drying process and to find the best way to preserve the quality of the wood, but for high efficiency. And this is the only way to just characterize in a way by using the water spectral pattern in the wood as a marker, as an integrated marker for this. Very interesting. So I really look forward for your future developments of your research.
Thank you very much for your comments and suggestions. Yeah, I will work harder.
Thank you very much.
So time is coming, so I will close this session. Thank you, Professor Ma,
Thank you very much.
for your interesting talk. So I will close the morning session. Afternoon session will start at 1 p.m., right?
Yes, yes.
Okay.
Thank you very much, Professor Takeuchi, for chairing the session.
Thank you for
Yeah.
Chenkova Sensei also.
Mr. Ma, just please make sure you have a question in the chat box, so don't oversee it, please. It's an interesting question. Yeah. So we are starting again at 1 o'clock sharp after the lunch break. We are starting afterwards with the poster sessions.
And you're the chair, right?
Yes.